Let's talk about weak acids. With strong acids, we saw that they dissociate completely in solution, and as a result, the concentration of H plus in your solution is equal to your original concentration of acid. There's no equilibrium there. However, with weak acids, we see that, generally speaking, if we have some weak acid HA, it will undergo an equilibrium in which it's separating into H plus and A minus. And so this is an equilibrium process. So it's not just a directly, okay, we finished the reaction. Some amount of your acid is breaking apart, and at the same time, acid H plus and your conjugate base are combining back together to reform your acid. And so this is an equilibrium process, right? And we're going to see that if we go ahead and establish the Kc for this, it will be H plus times A minus over HA. And this is assuming what is called, by the way, a monoprotic acid, although that is something we'll talk about later. So an acid with one proton. Although, again, we're going to see that we can say A and A minus as whatever we want. So we could say, for example, phosphoric acid is a weak acid. We could say that this is our equilibrium here. So we can set A to be, HPO4 minus, 2 minus rather. And, this would all fit, even if you have other charges and subscripts going on. Again, we look at things losing one proton at a time, so we look at one conjugate acid-base pair. But if we look back at that equilibrium expression, we see that we have a mathematical way of expressing it, right? And these specifically are referred to as Kas. So they are called acid dissociation constants. And you'll be able to see a large table of them on Discord in your extra resources tab. So you can see a variety of acid dissociation constants for various acids. And you'll see that, generally speaking, for strong acids, these Kas are above 1, meaning they very strongly prefer the products. Often they're very much larger than 1. But most Kas, because most acids are weak acids, are below 1. So you'll see ones ranging from 10 to the minus 1, 10 to the minus 5, 10 to the minus 13. We see that there's a variety of acids that dissociate to different extents. And we can kind of establish that by looking at the Ka. If we wanted to compare acids with higher Kas are stronger than acids with lower Kas. They dissociate to a greater extent. So the higher your Ka is, the more acidic you are. All right, and the lower your Ka is, the less acidic you are. And so, with this, with our understanding of how to use equilibrium constants that we studied last chapter, we'll be able to establish the pH and the H plus concentration of a weak acid. Let's take a look. When we're establishing this, say we have, let's say we're using acetic acid, and that's dissociating into H plus and acetate. HA turns into H plus plus A minus. A is just that kind of placeholder, a generic equation. And let's say we have, what is the pH? Here, I'll write it, let me move my equation down here, actually, and we'll write the question up top. What is the pH of 0.125 molar acetic acid if the Ka is 1.8 times 10 to the negative 5, which is about what it is for acetic acid. So we can figure this out. We have our equilibrium constant. We have our initial concentration of acid. That means we're going to use an ice table, just like before. So we're going to have our concentrations here. We're going to assume we have none of the others because we don't have any information about that. We generally ignore the ionization of water because water has a Ka of about 10 to the negative 14. So we don't really deal with the 10 to the negative 7. So we don't really have to deal with that in this example. So we're going to have our ice table. We're going to see clearly Q is going to be less than K, right? Because we have nothing of our products. But if we did, we would use Q like before and evaluate where the equilibrium is and how it's going to need to proceed in order to reach equilibrium. But for now, we can tell very clearly we have nowhere to go from 0 except up. So we'll get the following. And if we take a look at our Ka again, which was 1.8 times 10 to the negative 5, well, that's equal to x times x over 0.125 minus x. And a couple options here. Go into Wolfram Alpha, pop open your widget, and calculate it this way. Just put an x squared up here, solve it. You could do a quadratic equation on this. If you were to simplify this equation, set it equal to 0, you could do it a quadratic equation. Kind of pain in the butt though, why would you? But you could. Although, generally speaking, we are allowed to make an assumption. If we assume that x is less than about 5% of our initial concentration, we can kind of approximate that the minus x term goes away. And that makes the calculation a lot easier, right? If we can just do it this way, we can say x squared over 0.125. Ignore that minus x. If we assume it's less than 5% of our original molarity. And so that's the kind of rule of thumb. You're allowed to use this kind of simplification. You can always use Wolfram Alpha, get the real answer. But if we assume the 5% thing, that basically takes into effect sig figs. So if the x value is going to be less than 5% of our original molarity, then even subtracting it from our original molarity doesn't make sense with sig figs. So let's go ahead and solve it here, and then we'll do the Wolfram, and we'll see how accurate our assumption is. So 0.125 times 1.8 times 10 to the negative 5. That's we're going to just square root that to get our x value here. If we approximate, we get 0.0015. And indeed, if we go ahead and take that value, we always have to check that it's less than 5%. So 0.125, or rather, you should do it the other way, 0.0015 over 0.125. We see here again, that's obviously going to be less than 5%, but let's do it. Take this number, divide by 0.25. We get 1.2%. So we're okay to make this assumption. That value of x is so small relative to our initial concentration that we don't have to worry about using this approximation. We can say, okay, well, this is now our H plus, which is equal to A minus, and that's going to be our P, or what we can use to calculate pH. So therefore, since this assumption is valid right now, we can just do negative log has 0.0015, which is equal to negative log 0.0015, which is equal to 2.82. And that would be our pH of this solution. You can go ahead and check it with Wolfram. You'll see it will not be significantly different. All right, so this assumption that we made here, if we assume x is less than 5%, we get rid of it in the denominator term. We can just pretend it's not there because it's so small that it's not going to greatly affect our calculation. And so with that assumption, we saw that indeed this x value we got was less than 5% of our original concentration, so our assumption checks out. And as a result, we're going to be able to just use that assumption, make the calculation super easy for us, just solving for x squared as a square root, and then we can go ahead and calculate our pH. All right, in the next video, we'll look at this a little bit more.